1 month ago, the ground took less than a minute to bury thousands of people in Venezuela. Today, a much quieter question is spreading through engineering circles. One that has nothing to do with the fault line and everything to do with what was standing on top of it. Was the concrete actually strong enough to begin with? Not the concrete in some random building nobody checked. The concrete in a government housing program that has put roofs over millions of Venezuelans for the past decade, built with a type of cement that the country's own cement workers say was never supposed to hold up a building in the first place. Today, we are walking through exactly what investigators, engineers, and journalists on the ground have found in the 4 weeks since the earthquake, updating the death toll with the latest confirmed numbers and laying out precisely why this story is not over just because the shaking stopped. No guessing, no dramatizing, just the facts, the documents, and what the engineers are actually saying on the record. Before we get into it, drop a comment below. Have you ever lived somewhere and wondered whether the building you were in was actually built to the standard it was supposed to be? Tell me where. If you want to be the first to know every time something significant develops on a story like this, subscribe to the channel right now. It is completely free. A thumbs up helps the algorithm put this in front of more people who need to see it. So let's push for 5,000 likes on this one. Thank you. Now let's get into it. On June 24th, 2026, two massive strike-slip earthquakes struck within 39 seconds of each other in the Yaracuy region of northwestern Venezuela. The first at magnitude 7.2, the second, the true main shock, at 7.5. We covered the initial disaster in detail when it happened. What we are covering today is what has happened since, because a month is long enough for the emergency phase to end and the accountability phase to begin, and the numbers alone tell you how far this has come. In the first days after the quake, confirmed deaths stood at roughly 3,800. By the middle of July, Venezuelan outlets and international monitors were reporting the figure had climbed past 4,900, with more than 17,000 people displaced. As of this recording, the confirmed death toll sits above 5,300, with 16,700 injured and tens of thousands still classified as missing. The United States Geological Survey's own automated pager assessment system, which models likely fatality ranges within minutes of a major earthquake anywhere on Earth, had already flagged a real possibility the final number could exceed 10,000. This is what a death toll from a shallow urban earthquake actually looks like in the real world. It does not arrive all at once. It climbs week after week, as search teams reach buildings they could not get to on day one. And it climbed inside a country that had almost nothing left in reserve to absorb the shock. Nearly 8 million Venezuelans were already classified as needing humanitarian assistance before the earthquake struck, the result of years of economic collapse that had left hospitals running with minimal medical stockpiles and barely functioning equipment, even in ordinary times. When a disaster of this scale hits a health system already operating at that level of strain, every part of the response, from trauma care to disease prevention and displacement camps, becomes harder than it would be almost anywhere else on Earth facing the identical earthquake. And some of what those search teams found was extraordinary. 8 days after the earthquake, rescue workers pulled a security guard named Hernan Gil out of the rubble of the Galeria's Playa Grande shopping mall, which had collapsed on top of him. Gil had been sheltering inside a small concrete security booth when the building came down. And that booth, ironically, the one piece of reinforced concrete in the entire structure that appears to have held its shape under the load, is almost certainly the reason he survived 8 days trapped beneath a collapsed shopping mall. It took rescue teams from 7 different countries more than 3 days of continuous digging to reach him, after the access tunnel they had cut collapsed on itself multiple times during the operation, forcing crews to start over, working in shifts around the clock in stifling heat, above a structure that engineers could not fully guarantee would not shift again while people were still inside it. For 8 days, Gil's family had no confirmation he was even alive, and rescue coordinators have since described the moment his voice was finally heard, responding to a listening device lowered into the debris, as the operation's turning point, the moment that shifted the entire effort from a recovery search to an active rescue. Gil became a national symbol of hope in a country that badly needed one, and the government later awarded him the Hero of Venezuela medal. As of the middle of July, more than 2,400 foreign rescue personnel, over 31,800 government workers, and more than 30,000 volunteers remained actively deployed across the disaster zone. A mobilization on a scale most countries never have to sustain for a full month straight. But it is what happened at a different site, a residential complex rather than a shopping mall, that has turned this from a natural disaster story into an engineering accountability story. In the coastal town of Playa Grande, in the state of La Guaira, where roughly 80% of all buildings collapsed or were severely damaged, satellite imagery taken before and after the earthquake shows something specific happening to a cluster of apartment towers built under the Venezuelan government's Great Mission Housing Venezuela program a large-scale public housing initiative that has constructed homes for millions of Venezuelans over the past decade. Comparing satellite images from early May to images taken in early July, structural engineers reviewing the photographs for investigative reporters noted that several of the buildings in the Hugo Chavez housing complex appear to have sunk and tilted rather than simply cracked or sheared apart, the way a building typically fails when shaking overwhelms its walls and columns. According to one structural engineer who reviewed the imagery, that specific failure pattern, sinking and tilting rather than fracturing, points toward liquefaction. The phenomenon, where saturated sandy soil temporarily behaves like a liquid under intense shaking, combined with shallow foundations that were never anchored down into bedrock or a firmer soil layer using deep piles. Piles, heavy steel and concrete beams driven far below a building's footprint, are the standard engineering solution for exactly this kind of sandy coastal ground, precisely because they reach past the unstable surface layer into something solid enough to hold a structure steady, even if the soil above it briefly turns to liquid. The engineer's assessment, based on the visual evidence available, was that the buildings appear to have lacked that kind of deep foundation work entirely. At the same time this was unfolding, a second and in some ways more damning story was developing around the material itself, not just how it was built, but what it was built with. Orlando Chirinos, president of the United Federation of Cement Workers of Venezuela, went on record with a warning that should stop anyone reading it in their tracks. The type of cement widely produced inside Venezuela today, a domestically blended product known as CPCA1, is, according to Chirinos, suitable only for refractory work, plastering and flooring, not structural work, not the columns and load-bearing walls of an apartment building. He stated plainly that warnings about this exact issue had been raised by industry figures as far back as 8 years ago, and that Venezuela's cement plants had been operating at reduced capacity for years, with the country's ability to produce proper structural-grade Portland cement significantly diminished. Now, in the wake of a disaster that killed more than 5,000 people, residents in La Guaira are actively pressing the government to guarantee that the coming reconstruction phase uses genuinely high-quality, structural-grade materials rather than repeating the same shortcuts. Whether that demand is met will determine whether the next earthquake that hits this exact stretch of coastline produces a similar death toll or something closer to what we have seen in countries that take this seriously. The stakes on the funding side alone are enormous. The United Nations Development Programme's preliminary rapid assessment put direct physical damage from the earthquakes at approximately $6.7 billion, within a range of $4.7 to $8.7 billion, equivalent to roughly 6% of Venezuela's entire gross domestic product wiped out in under a minute of shaking. Against that backdrop, a government reconstruction fund reported at around $200 million, alongside verified international pledges, including roughly $150 million from the United States, routed through faith-based organizations and United Nations agencies, covers only a fraction of what full recovery will actually require. Every dollar spent on genuinely structural-grade material, rather than the cheapest available blend, is a dollar that has to come from a pool that is already stretched thin, which is exactly why residents in La Guaira are not just asking for better materials in the abstract. They are asking a government working with limited funds to make a specific, enforceable choice about where those limited dollars go. It is important to be precise here, because this is exactly the kind of story where it becomes tempting to skip straight to blame before the evidence actually supports it. And doing that would put us in the same category as the outlets we are trying to be better than. Investigative reporters, looking into the housing program's specific role in this disaster, have been careful to note that there is not yet enough centralized, building-by-building evidence to draw sweeping conclusions about the entire public housing initiative as a whole. Venezuelan civil society groups have separately reported, going back to 2016, that many developments built under similar programs were constructed without the required feasibility and geotechnical risk studies, a decade-old warning that reads very differently now than it did when it was first published. Getting even this much verified information out of Venezuela has not been simple. Several Venezuelan media outlets have shut down entirely over the past several years amid the country's broader economic collapse, and the outlets still operating and reporting on the reconstruction, several of them nonprofit and openly appealing to readers for financial support just to keep publishing, have had to piece this story together themselves, building by building. Because there is still no single centralized, authoritative damage assessment covering the entire disaster zone a month after the ground stopped shaking. What we can say with confidence, because it comes directly from a named industry official and named structural engineers reviewing dated satellite imagery, is this. Substandard structural cement has been in wide circulation inside Venezuela for years, despite warnings. At least one major housing complex shows a failure signature consistent with inadequate foundation work on unstable coastal soil. And the country as a whole was already in the middle of an economic collapse that had left building maintenance, inspection regimes, and construction oversight badly underfunded for the better part of a decade before the ground ever started shaking. Those three facts do not, on their own, prove that any single building's collapse was caused by any single decision. What they do prove is that the conditions for a catastrophic outcome were being assembled long before June 24th, one shortcut, one skipped inspection, one substituted material at a time. To understand why this matters so far beyond one shopping mall and one housing complex, you need to understand what liquefaction actually does to a building, because it is one of the least intuitive ways an earthquake can kill people. Under normal conditions, sandy soil that has been saturated with groundwater behaves the way you would expect solid ground to behave, firm enough to walk on, firm enough to support a multi-story building indefinitely. But when intense seismic shaking passes through that same soil, the violent vibration forces the individual sand grains to lose contact with one another, and the water trapped between them takes over, briefly turning solid-looking ground into something with the physical properties of a thick liquid. A building sitting on a normal, shallow foundation, one that was never engineered to reach down past that unstable layer, does not need to be hit by a stronger wave to fail. It simply needs the ground underneath it to stop behaving like ground for even a few seconds. Some buildings sink evenly and crack, others tilt, the way several witnesses and engineers have described seeing at Playa Grande, listing to one side as one corner of the foundation settles faster than another. Buildings anchored on deep piles driven into bedrock or a genuinely stable layer beneath the sand are far less vulnerable to this specific failure mode, because their support does not depend on the surface layer staying solid at all. Liquefaction has produced some of the most visually strange images in the entire history of earthquake engineering, and one in particular has been used to teach this exact concept in engineering classrooms for 60 years. During the magnitude 7.5 earthquake that struck Niigata, Japan, in 1964, several multi-story apartment buildings in the Kawagishicho district tipped over almost entirely intact, coming to rest tilted at angles of up to 80 degrees, essentially lying on their sides, while the buildings themselves suffered remarkably little structural damage to their walls or frames. The concrete had not cracked apart. The building had simply lost the solid ground underneath it as the saturated sandy soil liquefied, and the structure rotated and sank as a single, largely undamaged unit. That image, an entire apartment block resting on its side with its windows and balconies still intact, became one of the defining case studies that pushed the global engineering community to take deep pile foundations on sandy, water-saturated ground seriously as a non-negotiable requirement rather than an expensive extra. It is precisely the requirement that structural engineers reviewing the Playa Grande satellite imagery say appears to be missing from the buildings that sank and tilted in La Guaira 62 years later on the other side of the planet, in a completely different economic and political context, failing in a manner that is instantly recognizable to anyone who has studied that Niigata photograph. This is precisely why proper geotechnical investigation, the soil testing that should happen before a single foundation is poured, is treated as non-negotiable in seismically active regions with sandy coastal ground, the same kind of ground you find across much of coastal Japan, much of coastal California, and, as it turns out, much of coastal La Guaira. The cement side of the story is in some ways an even simpler engineering concept, and an even more damning one precisely because of that simplicity. Concrete is not one uniform product. Structural grade, Portland cement is manufactured, tested, and certified specifically to achieve the compressive strength required to hold up columns, beams, and load-bearing walls under the enormous stresses a building experiences during an earthquake. Lower-grade blended cements, the kind used for plastering a wall or finishing a floor, are manufactured to a completely different and far less demanding specification because nobody expects a plastered wall to carry the structural load of an entire building above it. Using the wrong grade of cement in a structural application does not necessarily produce a building that looks any different from the outside. It can look identical, pass a casual visual inspection, and stand perfectly well under its own static weight for years, even decades, because the difference only becomes catastrophic under the specific, violent, dynamic loading conditions of a major earthquake, the exact test that ordinary daily use of a building never applies. That is what makes substandard structural material so much more dangerous than substandard finishing material. It is invisible until the one moment it is tested, and by then it is too late to fix. In a properly run construction industry, this exact problem is supposed to be caught long before a building is ever occupied, through a process that has nothing exotic about it and has existed for generations. Fresh concrete is sampled directly at the pour, formed into standardized test cylinders, and cured under controlled conditions for a fixed period, typically 28 days, before being crushed under a hydraulic press to measure its exact compressive strength, expressed in units like pounds per square inch or megapascals. Every structural design specifies a minimum strength the concrete must achieve, and the testing exists specifically to confirm, batch by batch, that what actually got poured into the columns and load-bearing walls meets that number, rather than simply trusting the label on a bag of cement or the word of a contractor under pressure to finish on schedule and under budget. The strength of the finished concrete depends heavily on the exact ratio of water to cement used in the mix, the quality and grading of the sand and gravel aggregate blended into it, and how carefully it is cured while it hardens. Skip the testing, and none of those variables get caught if they drift from spec. A batch mixed with too much water to make it easier to pour, or blended with an inferior grade of aggregate to cut cost, can look, pour, and set exactly like properly specified concrete, and can support a building's own static weight for years without incident, right up until an earthquake asks that same material to do something it was never actually capable of doing. None of this is unique to Venezuela, and that is precisely the part of this story worth sitting with the longest. Engineering analysts comparing Venezuela's situation to countries with a strong track record of earthquake resilience, Japan chief among them, have been clear that no single material choice, on its own, determines whether a country survives its earthquakes well or badly. Japan's remarkable performance during major earthquakes is not the product of using one specific type of cement. It is the product of an entire integrated system, rigorous geotechnical investigation before construction begins, properly specified and consistently tested structural materials, detailed seismic reinforcement built into every column and joint, strict construction supervision throughout the building process, and continuous testing that catches problems before a building is ever occupied, all reinforced by some of the most demanding building codes and inspection regimes on the planet. Remove any single link in that chain, and the resilience of the whole system weakens. Venezuela's crisis did not remove one link. Years of economic collapse, reduced industrial capacity, underfunded regulatory bodies, and a housing program that, in at least some documented cases, skipped geotechnical work entirely, appear to have weakened several links simultaneously, which is a large part of why a shallow magnitude 7.5 earthquake was able to kill more than 5,000 people in a matter of seconds. If you are wondering whether this is somehow an isolated failure specific to one government program in one country, it is worth remembering that the underlying lesson connects directly back to something we have covered before on this channel. It also connects to something that happened a quarter of a century ago on the other side of the world, in a disaster that engineering schools still teach today as the textbook case of exactly this failure pattern. On August 17, 1999, a magnitude 7.4 earthquake struck the city of Izmit in northwestern Turkey, a densely populated industrial region east of Istanbul. More than 17,000 people were killed, and in the years of engineering investigation that followed, the story that emerged was disturbingly familiar. Post-disaster surveys found widespread use of undersized structural columns, missing or improperly placed reinforcing steel, and in a significant number of buildings, concrete mixed with unwashed sea sand pulled straight from local beaches, rather than the properly graded aggregate that structural concrete requires, a shortcut that dramatically weakens the finished material's ability to bond with reinforcing steel and withstand the specific loading conditions of an earthquake. Investigators also documented widespread bypassing of building permits and inspection requirements during Turkey's rapid, poorly regulated construction boom through the 1980s and 90s, contractors building additional unauthorized stories onto structures never designed to carry that extra weight, developers paying off or simply avoiding inspectors rather than correcting flagged defects. Several contractors and builders were later prosecuted in Turkish courts over specific building collapses, and the disaster became a direct catalyst for a wave of stricter building code reform across the entire country. But codes on paper are only as strong as their enforcement, and in the decades that followed, successive Turkish governments introduced what became known as construction amnesty programs, policies that allowed owners of buildings constructed in violation of code, including many built without proper permits or inspections, to legalize those structures retroactively in exchange for a fee, rather than requiring them to be brought up to standard or demolished. When a magnitude 7.8 earthquake struck southeastern Turkey near Kahramanmaraş in February 2023, killing more than 50,000 people across Turkey and Syria combined, investigators again found widespread evidence of the same underlying pattern: undersized columns, missing reinforcement, and buildings that had passed through those amnesty programs years earlier without ever being properly reinforced. Dozens of contractors, developers, and building owners were arrested in the aftermath. The lesson from Turkey's two earthquakes, 24 years apart, is not that stricter codes fail. It is that a code nobody enforces is barely better than no code at all. And that lesson is exactly the one emerging from La Guaira right now. When we walked through the contrast between the earthquake that struck Japan and the one that struck Venezuela within weeks of each other, the conclusion was the same one investigators in Venezuela are now reaching from the ground up. The magnitude of an earthquake tells you how much energy was released underground. It tells you nothing about what happens to the people standing above it. What determines that outcome is decided years, sometimes decades, before the ground ever moves, in soil surveys that either get done properly or get skipped, in cement that either meets a structural specification or does not, in inspections that either happen or get waved through. Every one of those decisions is invisible on an ordinary Tuesday. Every one of them becomes the entire story the moment a fault ruptures. So what does this actually mean for reconstruction going forward? And more broadly, for anyone watching this from outside Venezuela who has ever wondered about the building they live or work in, for Venezuela specifically, the path forward that engineering specialists are now recommending publicly is not a wholesale, unrealistic replication of Japan's entire system overnight, which nobody believes is economically achievable for a country already this deep into crisis. It is a targeted set of the highest value fixes, restoring domestic production of genuine structural grade Portland cement where it is required for load-bearing work, rebuilding real quality control testing on concrete batches rather than assuming a bag of cement performs to spec because of what the label says, enforcing modern seismic reinforcement detailing in every new structural design, not just flagship public buildings, requiring comprehensive geotechnical soil investigation for any major development built on the kind of sandy coastal ground that failed so badly in La Guaira, and reserving the most advanced and expensive protective technology, things like base isolation systems, for the buildings where failure carries the highest cost, hospitals, schools, and emergency response facilities, rather than trying to apply it everywhere at once. Whether any of that actually happens depends entirely on whether the public pressure building in La Guaira right now translates into enforced standards, rather than another set of promises that fade once the news cycle moves on. For everyone else watching this from a country that is not currently rebuilding from a magnitude 7.5 earthquake, the lesson is less about cement grades specifically, and more about a habit of mind. Most people never think about what is actually inside the walls and foundations of the buildings they spend their lives in. And most of the time, that is a reasonable thing not to think about. Because in countries with functioning inspection regimes, that work has already been done by people whose job it is to catch exactly this kind of shortcut before anyone moves in. But inspection regimes are only as strong as the institutions funding and enforcing them, and those institutions can weaken quietly, year after year, long before anyone notices, the same way Venezuela's did. If you live somewhere with any meaningful seismic risk, it is worth actually knowing a few basic things about your own building rather than assuming someone else already checked. Know roughly when it was built and under which building code, since codes are revised specifically in response to lessons learned from past earthquakes, and a structure built decades ago may predate reinforcement standards considered standard today. If you are ever in a position to buy, rent, or invest in property in a seismically active area, it is worth asking directly whether a geotechnical soil report exists for that specific site. Not a generic regional assessment, but a report for that exact ground, and whether the foundation design was based on it or simply copied from a neighboring lot. Pay attention to public reporting on your local building department's staffing and inspection capacity, because underfunded inspection agencies tend to fail quietly, long before a headline earthquake forces the failure into public view. If you notice diagonal cracking around windows and doors, visible tilting in a floor or a wall, or doors and windows that have started sticking or no longer closing properly in a building with no recent renovation, those are exactly the kind of visible symptoms that can indicate a foundation or structural issue worth having a professional look at, rather than something to dismiss as an old building simply settling. None of this requires becoming a structural engineer yourself. It simply means treating the building you live in with the same basic curiosity you would apply to any other major invisible system your life depends on. Here is the honest summary of where this stands 1 month on. The confirmed death toll from Venezuela's June 24th earthquakes has climbed past 5,300 people, with tens of thousands still missing, and international assessment systems have not ruled out a final toll well beyond that. A rescue effort involving personnel from dozens of countries pulled genuine miracles out of the rubble, including a security guard who survived 8 days inside a single surviving concrete booth. And running underneath all of it, investigators, engineers, and Venezuela's own cement workers are now pointing at the same uncomfortable conclusion that substandard structural material and skipped geotechnical work had likely been quietly accumulating risk across parts of the country's building stock for years before the fault ever ruptured. History gives us no shortage of precedent for exactly how this plays out from here. Turkey learned this lesson in 1999, wrote stricter codes because of it, and then watched enforcement quietly erode over 2 decades until a similar death toll repeated itself in 2023. Whether Venezuela's reconstruction breaks that cycle or repeats, it is not a question seismologists can answer. It is a question of funding, enforcement, and political will, playing out right now in La Guaira, largely outside the media spotlight that covered the earthquake itself for exactly 1 news cycle before moving on. We will keep tracking this as the reconstruction phase develops. Every new engineering assessment, every update on the cement supply, every figure the death toll climbs. Subscribe so you do not miss it. And leave that comment below. Tell me if you have ever questioned the building standards where you live, because the story we walked through today did not start on June 24th. It started years earlier, in decisions nobody was watching, and that is exactly why it is worth watching closely now. 5,000 likes on this one. Let's go. See you in the next one.